Unpacking your Android. This particular presentation itself is going to focus around how can we extract malware genomes from hardened applications. Within Android itself, we saw three main categories of hardening. One is obfuscation, another one is packing, and third one is a combination of both called protector. The techniques that we have would statically extract malicious genomes so that we can do a research around it and identify if it's vulnerable or not. But before we jump into the presentation itself, there is a quick disclaimer. So the views and opinions that I have expressed in this particular presentation itself is purely mine. And I would be really appreciate if we don't associate that with any of the companies or individuals that I'm associated with. So now that we have that out of the door, a quick who am I? So as I stated before, my name is Swapnil Deshmukh. I have co-authored Hacking Exposed series. So within the book itself, we basically talk about various avenues of how you can exploit, let's say, mobile, for example, or web application itself. What are the various attacks that we have, and how can we defend against those attacks as well? Along with that, I'm currently leading the security team for emerging technologies for a company called Visa. As a Moonlight project, I'm also working on a Poppy Seed project. This is an open source that we have that basically talks, it's an abstraction layer of all the different malicious applications that are out there. So we've found millions of samples for it, for various verticals itself. And we want to create a framework that will identify all the different malicious applications that are already out there for various verticals. It could be right from Android to iOS to Windows. So we started with Android at this given point itself because of the cost of deployment itself and the ease of use of it. And we have a running instance at this given point itself on malware repo, which is right at the end. So now that, why exactly are we here? Why does it matter at this given point itself? And the sheer reason why we started with this engagement was because we all are very easy targets. A lot of malicious applications are already out there in our trusted Play Store itself. It could be Google Play Stores. It could be Chinese Play Stores as well. They already are installed in there. In fact, there was a report that came out from Sophos that stated out 1 in 3 applications that was installed in 2017 from an Android app store itself was malicious. In some degree, it will collect our user data itself, or it could be a ransomware. So imagine 1 in 3 applications that we installed in 2017 itself can be malicious. That's a huge number. In fact, they continue reporting that there is billion-dollar industry when it comes to ransomware. There is one that we would be looking at. There was $33 million that they collected as a result of that ransomware itself. So very, very easy target, and they're earning millions and millions of it. So the biggest challenge is, why is it so difficult for us to evaluate an hardened Android application? And there are 4 different reasons or 5 different reasons that I can come up with. I'm very sure there would be more than that, because of which it's very difficult for third-party app stores to identify it. The first in the list is obfuscation. So obfuscation makes an application very difficult to read. What it does, it mangles the class names, it mangles the function calls itself, it will add Java reflections, it will do API hiding itself, which makes it very difficult for someone to read through the code. Anti-emulator is another one that makes sure that it's not running in a sandbox environment at any given point. So they will do something called proc info just to identify if it's running in a QMO environment itself or a sandbox environment. And if it's running in a sandbox environment itself, they will deflate their malware genome. A good example of that is Google Bouncer, which is used to identify any malicious content in Google Play Store itself. Heavily uses it uses emulator itself to identify a lot of applications. And they have 2 criteria. They run in a sandbox environment, and they only test that application for 5 minutes. So as a malicious author itself, what would be the workaround that we can come up with? It's very simple, right? Have a delay of 5 minutes. Or if it's running in a sandbox environment itself, do not inflate your malicious content. And you pass through your Google Play Store. So it's as easy as that. Along with that, there's root detection checks that make sure that you're not running in a compromised operating system. So Google coined the term called root to make sure that if it's elevated privileges that you have, then it will, again, look for certain conditions itself. If it satisfies that, then it will make sure that it's not able to execute the malicious content itself. Or you also have anti-debugging as well. So as a security researcher, a few prerequisites that you have to even analyze any code dynamically is that you have to first root the device. That's the first thing that you need to have. And the second thing is you need to have some sort of debugging controls in place to hook into a GDB, for example, or do some method swizzling to just do a log dump of what exactly is the application trying to do at any given point. What are the calls that they're making? What are the functions that have been called out of it as well, right? So you start logging that just to analyze as well, right? So by having root detection checks and anti-debugging checks, as a security researcher, they're not able to analyze this application further. In 2017 itself, we saw a huge trend. So there's anti-tampering solutions, which make sure that each code blocks would have their checksums. And if you modify any of those checksums at any given point itself, any code blocks at any given point itself, your checksum would be different, which means that the application is tampered with, right? So as soon as it detects that the application is tampered with, they will make sure that the malicious part of the application is not running. There is also a new trend in later half of 27 that we observed called white box cryptography. What it does is it encrypts a part of the Android code itself. And the key that has encrypted this data would be completely obfuscated. And that obfuscation piece would be spread across the heap itself. So if you want to decrypt the data, or if you want to statically analyze the code itself, you first need to identify what the key is, and then you can do a dump of that part of the malicious file, whatever has been encrypted. So it makes it a little difficult for us to even analyze it further. Along with that, white box cryptography is also being used for ransomware as well. So they will encrypt your entire SD card, and they'll say you have to pay 0.5 bitcoins in order to decrypt this data. And if you try to decompile an application to identify where the keys are, it would be sprayed across the memory itself, making it difficult for someone to gather that, right? So malicious authors are finding avenues like these to bypass a lot of checks that we have in place by the third-party products or by Google Play Store itself to publish that in Play Stores. As a result of that, we have seen a huge surge in malicious applications itself being out there. So now that being said, this is not the first that is talking about this particular topics itself. There are a bunch of them, a few listed there. There was a talk in DEF CON last year talking about how to hack into Android itself when it's been hardened, when the application is hardened itself. Unfortunately, the tools that they have released as an aftermath of that itself, aftermath of their presentation, it's all been obsolete at this given point or are not been maintained. As a result of that, there is no concrete evidences of us just downloading something from GitHub and decompiling an hardened application itself, right? So that's where the initiative came in from for the Poppy Seed project. We are certainly looking for contributors itself. There are a lot of data that is already, or a lot of research that is already out there. We should all consolidate that in one place and then use that to identify the application itself. So we talked about the premise so far around the hardening of application itself. Let's quickly take a look at the first hardening technologies that we have seen for Android, which is obfuscation. As I stated before, obfuscation is basically scrambling of your data. A good example for that is, let's say if for an Android class, you have com.owasp.password validator. As a human inspecting it, it's very clear that this could be a password validator class files, right? So obfuscation will change that. It will just change that to com.h.s. So as a human, it's a little difficult for us to understand by just reading the class name itself. And you have to inspect that class name class further to understand what that class is actually trying to do. So obfuscation would basically mangle those things. There are a few other things that they scramble. They also scramble the variable names, the function names. They can also do a control flow obfuscation as well. So if you have try catch, if you have if else statement itself, they will change that into a switch. And that switch would have a dead code. So you have to go through each cases itself to understand what are they trying to do there There could be a variable that is returned back that can be used by some other case statement itself to execute certain payload of it. So since because of that dead code injection itself, it becomes very difficult for someone to like read through that code. The third in the obfuscation standpoint, third in the obfuscation that we have looked at is called string encryption. So it will encrypt the string, and in order to decrypt the data itself, they will have some logic inside the file on how you can decrypt that string. So as a human, when it's reading a jargon strings itself, it's very difficult for us to understand what it is, right? So now you have to go through the entire call flow itself to understand how you can decrypt that file, decrypt that string itself to get a human readable string. So obfuscators would do all of that. Along with that, they also use Java reflection, either for an API hiding itself or adding more complexity to the code. The only good thing about this is they are not encrypting any of the malicious genome itself. The malicious genome is along with the code. So if you want to read through the code itself statically, then you have to read through through the code itself. And the first in the example itself is ProGuard. So this is an example of a very lightweight obfuscation technique. It comes out of the box from Android standpoint itself. And as you can see, this is one of the ransomware. So the first part of the code itself is basically used to lock a computer, lock a device. So it will lock a device, it will set a passcode for it. In order to decrypt the data, you need to enter the same passcode. So if you decompile the application once you get it, it was very evident that the passcode is set to 1008. From a malicious author standpoint itself, they were quoting 0.5 bitcoins for this. And when we did some stats around how much they earned over a period of time, till last week, they earned $34 million from it. So by just having a decompilation of the application itself, it was very evident that the passcode is right there, and we could have helped millions of people who paid for the ransomware itself to unlock their device. So that's one example. Let me just talk about a quick obfuscation technique as well. So if you look for classes.forName, which is com.h.s, that is a kind of an obfuscation for class names. So it's not very trivial, as you can see, to read through what exactly a malicious author is trying to do at this given point, even if they're using some sort of obfuscation. But then it gets complex. The second in the list is Dex Protector. Dex Protector is a combination of packer and obfuscator. At this given point itself, we will just look at the obfuscation techniques and how they're obfuscating it. So the one that is highlighted is basically a Java reflection where it calls onCreate with certain arguments that have been passed. This onCreate, when you look at the file itself, there were 9 different instances of it with various arguments being passed. And each and every argument was called. So each and every method was called by passing various arguments to it. It will collect a small bit of code and it will pass it to the other one itself. By collecting all of this, you basically have a decryption key. But if you have to go through 9 different methods to understand how to decrypt the data itself, it's very time consuming. So as a result of that, we created a Python script that will basically go through the entire code, start dumping the data bits in the data bits, and then collect the decryption key and use that decryption key against entire decompiled class files itself to first remove the dead code and also give you a decrypted string. So as a result of that, we use that Python script to just understand which method has been called by that function. So it was calling dexprotected.name, which was one of the loaded libraries that they had, and they were passing an argument for run along with a small hash, and that hash was collected through the string encryption mechanism that we have. Along with that, it was after it calls that, it looks for certain attributes for root detection checks or for anti-debugging checks itself. If it passes through that, it basically calls the next function. So as a person who's trying to research on malware itself, I know that the next jump that they would be having, provided all the conditions are satisfied, is the activity splash itself. So now I don't have to go through 9 different method calls to understand what they're trying to do. All I need to do is I just need to know the next jump that they have. Very similar to how we have it for the assembly language as well, right? We just go through each assembly language. We know which the next jump would be provided certain conditions have been met. So we try to do the same thing itself. So index protector, this was the next one that was called. And they had a function that was called from the malware genome itself. So now we know how to reach out to it, right? So if you basically have a Python script that can help you out with this. The next in line was for a premium SMS malware application. So this particular malware application itself would send out SMS to a premium SMS numbers itself, and it will send out various data. It could be right from your geolocation, or whether you are close to home or close to office, or the time whenever you just leave home. So it will send all of this information back to a premium number itself. And when we looked at the code itself, as you can see, we cannot see where the premium number is stored, right? Because they all are being encrypted. The method names are being encrypted as well. However, for each and every calls that they have, they were importing a file, and they were importing this hhhh.whhw. So that particular class name itself had the logic of how to decrypt the string or the function calls. So now, for us, the next step would be just to jump into that call itself, right? And that's exactly what we did. We jumped into it, and we saw that they're basically passing 3 different arguments to it. They're passing a string that needs to be decrypted. They're passing a number, and they're passing another character. And the function, if you further inspect the function itself, they're doing 3 things. They're doing an AND, or, based on the number of numbers that have been passed in the middle argument, the second argument, and they're decrypting based on that. So we mimicked that entire call function itself into a Python code, and we said, okay, let's just do this. All the encrypted functions that we have, or the string, just pass it to this particular function call. There are 4 different results that it will have, and one will have a human readable code. So if we get one human readable code itself, we know that that's the logic that they use to decrypt the string. So without even understanding the entire logic itself, without even spending a lot of time into how they are trying to do it, we basically just mimic that code, and now we are able to extract all the code from there. Now that becomes very easy for us to read the code through, right, at that given point. So that's another instance where you have in-file encryption mechanisms to pull the data out. Now, the second hardening technique that we have seen is called Packer. Packer would basically encrypt a section of the code, and it will keep that in the memory. If all the conditions are met, then it will decrypt that data and pull that information from there. It could be malicious content, or it could, in many different companies, it's been used to it's used as a secure storage of the data, or where the IP is very important, they use Packer to encrypt that data itself. So in case of Packer, they are doing it in 3 different ways. There's the dynamic code modification, where you're modifying the code itself on the fly based on the certain conditions, whether they are met or not. Then you load that file in the memory itself, or in certain cases within your data drive, or there could be an in-file loading as well. So conceptually, this is how it works. You basically have a APK file, which is, before signing it, you upload that on a website somewhere, and it will modify your manifest file, and it will modify your classes.dex, which has all the logic around how the code would actually work. And it will give you a new classes file, which is called a stub. So the first avenue of calling an APK itself is that it will go to the manifest file. It will look at where the stub has been loaded. It will load that stub in the memory first, look for all the conditions, whether it's satisfied or not. If the conditions have been satisfied, then it will load the main classes.dex that was written by the malicious author. So the first in the example that we have was released out in December 2017. And this was a packer called JumpJ2. I'm just making up the name at this given point itself. I don't know the name of the packer, but we found this one where the class name and the header size, if you look at, it's normally close to 46 or 62 bits, right? And this was close to 136 kilobytes. So that's like a huge chunk of data, right? So we started inspecting why exactly does it store that huge of a file, and it was dumping that from a header bytes as well. It turns out that they were storing the classes by classes.dex, the malicious classes.dex in clear inside the header files itself. So now the next step would be just to dump that file, store that as a classes.dex, and decompile it, right? And that's what we did, and we were able to extract all the files. So security through up security itself, but at least we were able to like pull the data out without installing it on any phones or doing a lot of analysis around it. The second is more dynamic in nature. It's called Outcry Infiltrate. Again, we are not very sure on the file name itself. All of these names are named based on the class files it loads. As I stated before, the first step in the process is to modify the manifest, right? And the first injection point that you have for Android is your application tag. So that's exactly what we did. We looked at the application tag itself, and it turns out that they're calling the one that is highlighted, it's calling Android support multi-dex and multi-dex application itself. The multi-dex application that it's calling has the call for the stub. Now, again, another classic case of security to security. They are making it sound like this is an Android SDK that they have downloaded. That wasn't the case. This particular file that they have is actually something that they embedded along with the Android SDK itself that has the call for the stub. As a result of that, so we went to Android, multi-dex application file itself, and we saw that it's calling outcry. It's calling outcry with a hash to decrypt that data, the one that is highlighted below. So, like any sane person, we followed the trail and we said, let's just go to the load library that they have. And the infiltrate call itself basically uses that as a hash, and it sends to a dynamically loaded library called second hand. The second hand, again, does all the checks and balances to make sure that it's running on a secure environment itself. It's not running on a rooted device. It doesn't have the anti-debugging check itself. And in order to decrypt that classes.dex, it provides you with that hash. That hash was the key to decrypt that data. So we created all the knobs for all the different conditions that we have for root detection checks or anti-debugging checks itself. And then you are left with the file and how to decode, to decrypt it, right? So we found an easy avenue of it. We patched the second hand .so library that they had, and then we finally reach out to the main classes.dex that was loaded in the memory itself. And we said, rather than you loading in the memory itself, store it here so that we can grab it. So we grabbed the classes.dex from there itself. And once we had it, we just decompile it and we just get the code, the malicious code right there, right? So that's the second one that we saw from a packer standpoint. The third in the list was called Wiki. This is another one that was encrypting SD card. So it will encrypt your SD card itself, and the logic of encrypting the SD card was within the file itself. So we used the same process. We looked at the manifest file first. We saw where the injection of that stub actually is. And we found that the injection of the stub was at a VG application, which is extending the Android's application at this given point. And it was calling two different SO files. The first SO file was to make sure that it's checking for all the different conditions that we talked about before. And the second one was a wrapper that would basically decrypt your data. So we said we can use the same techniques that we used for Outcry, where we bypass all the different conditions to check whether the files have been validated or not. And then we use the decryption key to decrypt the classes.txt. But the interesting thing was there was no code to decrypt that data. So as you can see, there's no hash function. So if I go to the previous slides itself, this particular function was calling the load file along with a decryption key. So that was the decryption key right there, right? So condition satisfied, use this decryption key to dump your classes.text. In Wiki, sorry, I'm going the wrong way. So in case of Wiki itself, there was no decryption key at this given point. So, and we said if we run the elf hook.so, obviously the conditions would not be met, so we would never be able to get the decryption key. But they were doing one interesting thing. What they were doing at any given point itself was they were storing the file, the classes.dex, in files folder. And during the course of the application, whenever you're running it, it will stay there. And when you run the application again, so when you relaunch the application again, so it will delete that file again and then recreate it. So we said, okay, let's just launch this application on a non-rooted phone itself, do a ADP backup, which does a backup of the files folder. Let's just take that file folder out. There would be a classes.dex in the files folder itself. We can use the same decompilation techniques that we know of to get the real Java code that has the malicious code. And that's exactly what we did, and we were able to get the classes.dex, the malicious classes.dex. So there are avenues like this that basically helps us out, pull that information from there. So the last in the hardening techniques that we have is called protector. Protector is basically a combination of both a packer and an obfuscation. So it uses the encryption of classes.dex, and it also obfuscates the logic of how you can reach out to the stub itself. So as we saw in the obfuscation itself, it makes very difficult for us to read the code itself in many different ways. So that's exactly what happened with us. So this is how it works under the hood. You have the same techniques that you have for packing, exactly the same process. The only distinction that they have is that they have obfuscated the stub and how they're calling it. So now we come back to Dex Protector. We looked at it from when we were looking at obfuscation itself. And we used the same techniques that we used for Packer to decrypt the data. So the first thing that we did was we identified the application and where it's been called. So we identified that it's calling COM, Android, GMS, COM API application. And we know this for sure that it's security through security. They're just injecting their code in the Android SDK that they call it's an Android SDK kind of a thing, right? So we did that. And now we know how to decompile, deobfuscate in a way the code that is already obfuscated, right? So we did that, and we deobfuscated that code, and we identified two variables. We said, okay, they're calling this load library itself, very similar to how they're doing it for Packer. And after that, the next step that they call is a different file. So we said, okay, skip the first two steps where you're doing the validation part of it and directly come to the third part where you're basically launching that malicious content. And that's how we were able to identify what that application is trying to do by running it on a device. By doing this particular control, by doing this particular check itself, we identified that there is a malware called TZ, which was impacting Android users. And in fact, Google came up with the finding itself in August or September of last year. So that's various techniques that we have seen from a malicious standpoint itself. So the Poppy Seed project that we have has identified 46 such different obfuscators, packers, or protectors. And as you can see, each and every protector is treated differently, right? Or the obfuscators or the hardening technologies are treated differently. And we are creating use-by-use Python scripts that can be injected. So the first phase that we have within our project itself is to do a discovery phase of it. So after discovering, or rather, after discovering itself, we identify whether they're using an obfuscator, protector, or a packer. Once we have identified through that itself, once you do the discovery, then you call that particular file that we have created for deobfuscating the code. So a good example of that is, let's say for TZ application, they're using Dex Protector. By now that we know that they're using Dex Protector itself, we now know techniques of how we can deobfuscate the code to make it more human readable. And now we know how to decrypt the data as well, right? So we use that logic in a Python code so that you can decrypt that data completely and understand what genomes are they using. So during our during the start of the call itself, the presentation itself, we talked about various samples, right? And that's where the samples are so important for us. By identifying all of the samples itself, we were able to find 456 different Android genomes that are being implemented in an application at this given point. So we said, that's awesome, but how is that beneficial for all of us, right? So we are going to create a static engine for the same so that they can do a static analysis for you. And after that, the next process is to scan the entire Play Store, all the Play Stores that are out there, and identify this malicious content itself and report it to Google so that they can do the right thing after that. So that's all from an Android standpoint itself. Interestingly enough, there is an IoT application that we all must have heard about for sure. And we are looking at the security posture of it. And interestingly enough, we found that they are sending sensitive information from our home devices itself to a particular server. Again, we haven't inspected a lot in it. It was just day before yesterday that we found it. So maybe we'll have some more details soon. But as you can see, it's basically calling home with the username, the port, and the password. And it basically sends out your information, a user information about certain activities that we are doing at any given point. So once we have done the inspection around it, I'm happy to release it out so that we all can understand the security posture of it. So that being said, time for questions. I want to open up the floors for what we have seen so far, or any observations or any feedbacks that you have. Sure.
Hello. So I'm curious about the obfuscation tools. Are there makers on the black market building these and evolving them and selling them?
So from an obfuscation standpoint itself, we haven't seen anything of someone creating it. But for packers, we certainly have. Like the outcry that we saw, or the JP2 that we looked at, those were created by black market for sure. For obfuscation, they're using off-the-shelf product at this given point. We have seen DexGuard, we have seen Dex Protector. There's a Guard Square, one of the vendors that we have. We have seen that being used for malicious contents as well. But we haven't seen any new thing from an obfuscation standpoint coming out.
Yeah, from the obfuscation point of view, like there are different levels are there, like 1, 2, 3, 4. So the one that you have tested, is it like level 1, or which level is it? Or if I'm using the highest level, I'll be more secure?
Fair. I'm not sure what different levels are,
Okay.
but there are different techniques that you have for obfuscation. Like you have class name obfuscation, which is like the bare minimum that ProGuard provides you. But there are class name encryptions, there are API hiding, there's Java reflections. So what we have looked at is like a combination of all of them used together.
Yeah, because when I was doing obfuscation, so there is like easy or medium or very strict or very high level there is. So I just want to know like which level you have done. So if I do like very highest level, then will I be secured?
I see.
Yeah.
So as I stated before, I'm not very sure about the different levels itself. We have seen two different things. We have looked at all of the different features being used from an encryption, from an obfuscation standpoint, and there is iterations. So you can do it 1 time, or you can do it 50 times, or you can do 600 times, and it will obfuscate based on that, right? So that's all that I have seen. So I'm not sure how to map that to the level 1 or level 4 that you talked about.
My question is like,
Sure.
if we were to find a pattern, like if I create a sample code and then I try to obfuscate it and then I try to analyze how it is doing it, is it like similar, like kind of research if we do it, over a period of time, would I be able to know like how they do it? So
True, we can certainly do that. So from our engagement standpoint as well, we try to do the same thing with DexGuard, because we are not able to crack DexGuard at this given point itself. So we wanted to know how exactly are they trying to do it. And we used right from 1 round to like 600 rounds to understand how the code would change based on that.
Yeah.
So yeah, that's part and parcel of the research as well.
Okay, thank you.
Sure. Hey.
Legitimate
we have
apps
to-
obfuscate their code? Like I was just wondering if the level of obfuscation be an indicator of high probability for containing malware.
True. So it's actually not. Even the apps that we use on a regular basis as well, they do obfuscate it. So anything that has like an algorithm or an IP that they want to protect, they normally would go for obfuscations. They also, so there are a few companies that I know of which are also using white box cryptography to just give you a secure container as well. And they all are legit applications. So that should not be the parameter of like us assessing whether it's a malware or not.
Is there any tool to compute the level of obfuscation?
So out of the box, a lot of applications do that. So as I stated before, DexCard, for example, gives you avenues of how many times you want to obfuscate it. So that kind of has a level of difficulty associated with it. There's few others that we talk to as well that provides you with the same option as well.
But can you measure it, like looking at the
So
compiled code?
once you have compiled the application itself, it's very difficult for us to measure it from a security research standpoint itself. But if you're a developer, then you can certainly have quantification around it.
How many of these applications are actually using white box cryptography, and have you had success in attacking these implementations?
So in last year itself, we saw 3 different applications using white box cryptography. They all were under the ransomware category itself. And they are trying to implement their own white box cryptography in many different ways, which is making it a little easier for us to understand what they're trying to do. But I'm very sure it will get sophisticated as we go along. Awesome. So that's all that I had. Thank you.